Hello everyone, my name is Ayush Singh, pursuing BE from Sri Venkateswara College of Engineering, and today in this video we'll be talking about CAD. What is CAD? CAD or Computer Aided Drawing and Design is a comprehensive approach to the design and engineering process that utilizes digital tools and technologies. It encompasses a wide range of software applications, including computer-aided design (CAD), computer-aided manufacturing (CAM), and computer-aided engineering. To name a few, these specialized software programs allow users to create, manipulate, and analyze digital models of their designs, streamlining the entire design and production lifecycle. Projection of points. Orthographic projection. The most fundamental CAD technique is the orthographic projection, which involves representing a three-dimensional object on a two-dimensional plane. This is done by projecting the object's point onto the three principal planes: the front, top, and side views. Isometric projection. Isometric projection is another common technique used in CAD where the object is rotated 30 degrees along each axis, resulting in a three-dimensional view with equal length axes. This provides a more realistic representation of the object's proportion and dimensions. Perspective projection. Perspective projection simulates the way the human eye perceives depth and distance, creating a more realistic and visually appealing representation of the object. This technique is particularly useful for architectural and product design visualization. Orientation of points in quadrants. Quadrant first. In the first quadrant, both the x and y coordinates are positive, representing points in the upper right region of the coordinate system. This is often the default quadrant for many CAD applications, as it aligns with the typical orientation of technical drawings and models. Quadrant 2. The second quadrant has a negative x coordinate and a positive y coordinate, representing points in the upper left region. This quadrant is less commonly used in CAD, but can be useful for certain types of symmetrical or mirrored designs. Quadrant 3. The third quadrant has both negative x and y coordinates, representing points in the lower left region. This quadrant is often used for representing underground or subterranean structures, or for modeling complex systems that extend below the ground plane. Quadrant 4. The fourth quadrant has a positive x-coordinate and a negative y-coordinate, representing points in the lower right region. This quadrant is commonly used for architectural and product design visualization that require a downward perspective, such as floor plans or views from an aerial angle. It allows designers to easily showcase different layers or levels within a structure. Projection of lines. Parallel projection. In parallel projection, lines are projected onto the drawing plane in a parallel manner, maintaining their true length and direction. This is the most common type of line projection used in CAD, as it provides accurate representations of the object's dimensions and proportions. Perspective projection. Perspective projection, on the other hand, simulates the way the human eye perceives depth and distance, causing lines to converge at a vanishing point. This creates a more realistic and visually engaging representation of the object, but requires more complex mathematical calculations. Axonometric projection. Axonometric projection is a hybrid approach that combines elements of both parallel and perspective projection. It maintains the true length and direction of lines while introducing a degree of depth and visual perspective, resulting in a more dynamic and informative representation of the object. Projection of planes. Horizontal planes. Horizontal planes such as floors and ceilings are typically projected onto the drawing plane with their true size and shape. making it easy to determine the dimensions and layout of a design. Vertical planes. Vertical planes like walls and partitions are often projected in a way that shows their true height, while their length and depth may be foreshortened or distorted to create a more informative perspective. Inclined planes. Inclined planes such as roofs and sloped surfaces require more complex projection techniques to accurately represent their shape and orientation within the overall design. CAD software can handle these challenges with ease. Curved surfaces. The projection of curved surfaces like domes, arcs, and organic forms is a particularly challenging aspect of CAD, requiring advanced mathematical algorithms and specialized software tools to achieve realistic and accurate representations. Software used in CAD. One of AutoCAD. One of the most widely used CAD software, AutoCAD, is a powerful 2D and 3D design and drafting tool used by architects, engineers, and designers across a wide range of industries. SolidWorks. A leading 3D CAD software, SolidWorks is renowned for its robust modeling capabilities, enabling users to create complex, high-precision 3D models for a variety of applications. Revit. Revit is a building information modeling software widely used in the architecture, engineering, and construction industries, allowing for the seamless integration of design, analysis, and construction processes. SketchUp. SketchUp is a versatile 3D modeling software that is particularly popular among designers, architects, and hobbyists for its intuitive user interface and powerful visualization tools. Conclusion. CAD has revolutionized the way designers, engineers, and architects approach their work, providing them with powerful tools and techniques to create and visualize their ideas more efficiently and effectively. From the fundamental concepts of point, line, and plane projection to the specialized software that drives the CAD process, this field continues to evolve and shape the future of design and engineering. As technology advances, the possibilities for CAD will only continue to expand, offering new and innovative ways to bring even the most complex ideas to life. That was for the theory part. We will be moving to solid edge and we'll be solving some problem. Okay, now we will be solving one lines problem and one planes problem on solid edge. So the first question is a line AB is 75 mm long and it is 30° and 40° inclined to HP and VP respectively. The end A is 12 mm above HP and 10 mm in front of VP. Draw projection line is in first quadrant. So first we have to take offset above HP, which is 12 mm. So we will put the distance as 12 mm and here we have 12 mm. Now we will take another offset of 10 mm below VP. We'll put a smart dimension, sorry, not a smart dimension, this distance between, and we will measure the distance between them. So yes, it is 12 mm and 10 mm. Now we have a line AB 75 mm long and it is 30° and 40° inclined. So it is above HP, it is inclined 30°. So we will take thin lines. Now we'll put the length as 75 mm and angle as 30°. Same for the below HP. Uh, Same for the below HP, we will put the length as 75 mm but the distance, sorry, not the distance, the angle will be minus 40 degree. Now we have to create a lamina. On both of the ends of lines. We can mark them as A, not caps, A and B. Similarly for the below VP also, A and B. Now true lengths are already given. We have to find the apparent length. So to find the apparent length, we'll be using, we have to draw one line. We have to move it through, make a perpendicular to this 10 mm lamina we have drawn. Not this one, sorry. Yep. Now we will take here arc by center point. We have to take A end of the below VP as center, and this perpendicular we have drawn as another end. So now we have to intersect this locus we have drawn. Now we can see it is intersecting somewhere here. So we will trim the unwanted part, and now we will join these two as thin lines. Similarly for the below VP, we will use the same as it is. We will draw a perpendicular, take arc by center point, and now we will bisect the loops. We will trim the unwanted parts, and we will join the ends. By using smart dimension, we can see the length of both of the. Okay, so the apparent length is 57.45 for the above HP, and for the below VP we have 64.95. We can mark the arrow in the direction we have drawn. And also denote the angle between the two lengths also. Okay, now this problem is completed. We'll move to the next problem. So the question is, a pentagon lamina of edges 25 mm is resting on HP with one of its sides such that the surface makes an angle of 60 degree with HP. The edge on which it rests is inclined at 45 degree to VP. Draw the projection. So first we need to draw a pentagon. For pentagon, we have the outside angle as 72. So first we will draw the base of the pentagon. We'll put the length as 25 and angle as 72. For the next side we'll use the same length, but the angle would be 72 into 2. Similarly, as we go, turn 72 into 3, 72 into 4. Now we will convert this to thickness. Okay, we will rotate this pentagon. Sorry, not. Using thick lines, we will mark it on the XY line. You can denote the sides of the edges of the pentagon as here A, B, C, D, and E. For here, B is visible, but E is not visible. So we will be putting B dash in bracket. We will be giving A dash. Similarly for C also, C is visible, but E is not visible. So we will put C dash in bracket E dash. Now in the question it is given that the surface makes an angle of 60 degrees with HP. So we will be selecting these lines and we will move it. We will rotate this lambda to 60 degree. Rotation angle we will give as 60. And now by using this perpendicular toolbar, we will perpendicular this line to the XY line. Now we will extend these lines by thin lines. Now we will extend these lines also to make the second diagram. Now we will join the lines using thick lines. Here A, B, C, D, E, and A. We can trim the unwanted lines. You can now denote these edges also. This one's A, B, C, D, and E. We can follow, like, we can give the leader lines. to denote. Now we'll move to the third part, which is the edge on which it rests is inclined at 45 degree to VP. We will take a line of, we can take a thin line, and we'll put the angle as 225, sorry, length as 70, and angle as 225. Is it 45 degree? Yes, it is 45. Now we'll select the second figure we have drawn, and we will, before that, we will put a reference point of 2 mm somewhere in this. Okay, now we will select this pentagon, and we will move it to, now we have to rotate this. So we'll use the rotate function. Now we will rotate the axis. Now we will extend these lines. So we will be intersecting somewhere here. A will be intersecting somewhere here. Similarly, C will be intersecting here. D here. Now we will join all these lines with thick line using thick lines. We can denote the edges as B dash, A dash, E dash, D dash, and C dash. Okay, this problem is not completed. Okay, this was the problem. Yes. So that was all for this video. Thank you.